Hello students, welcome back to Engineers Academy. Do hit the subscribe button if you are here for the first time. Now we are going to solve these two problems, which says that the metal stud punch is subjected to a force of 120 Newton on the handle. Determine the magnitude of the reactive forces at pin A and in the short link BC. Also determine the internal resultant loadings acting on the cross-section passing through the handle arm HD. So we have to find the internal loadings at the cross-section through D, and we are also required to find the resultant internal loadings acting on the cross-section passing through the handle arm HE and across a section of the short link BC. So first of all, we are required to find the reaction forces at pin A and the force in this short link BC. So now as you guys can see that if this handle is subjected to 120 Newton force in this direction, so what it will do is that it will apply the force on this BC link in the upward direction like this. And as a reaction, this BC link will apply the force on this handle in the downward direction. So if we consider this handle as a free body diagram, so that BC link will apply the force on this handle in the downward direction. So let me show that force here. So this will be force of BC link. So this will be FBC, and at A we will have the support reaction. So let's say that we have AX here, we have AX, and we have AY in the vertical direction. So we are required to find, in the first portion of the problem, we are required to find AX, AY, and FBC. So if we apply the sum of the moment about point A, the sum of the moment about point A, that must be equals to 0, and the counterclockwise moment is assumed to be positive. Now as you guys can see that if you want to find the moment about A, both of these are passing through point A, so they are not going to produce the moment about point A. This 120 Newton force is producing the clockwise moment about point A, and to find the moment of this FBC, we need to resolve this into its components because we do not know this distance between point A and B. Let's see if I draw a line here. So this red line is perpendicular to this line, and if I draw another line, this horizontal line, this line is perpendicular to this line. So this angle is 60 degrees. So if this is 60 and this is 90, then this angle is 30. So we can say that this angle is 30 degree. So now we can resolve this FBC into its components. So we will have one component of FBC in this direction, and we will have one component in this direction. So this component is the cos component. So we can say that this is FBC cos of 30 degrees, and this one is the sine component, but it's passing through that point A, and we want to find the moment about point A. So the moment arm of this component from that point A is 0. So only the cos component is producing the moment about point A. So we can say that this FBC cos of 30 is producing the counterclockwise moment about that point A. So we will write plus FBC cos of 30, and the moment arm of this component from that point A is this distance, which is 50 mm. So 50 mm divided by 1000. So 50 divided by 1000 will be 0.05. So the moment arm is 0.05 meters. Similarly, this 120 Newton force is producing the clockwise moment. So you'll write minus 120. And the moment arm of this 120 Newton force from that point A is this distance. So this distance is the perpendicular distance, right? So this is 200 plus 300. So this is 500. So 500 divided by 1000 will be 0.5. So 0.5. So we'll multiply this with 0.5 meters. This is equal to 0. And from this, we say that FBC is equal to plus 120 into 0.5 divided by cos of 30 into 0.05. So we can say that 120 into 0.5 divided by cos of 30 multiplied by 0.05. So FBC is equal to we can say 1386 Newton. So FBC is approximately equals to, let me write it up to 2 decimal places. So this 1385.64 Newton. Similarly, if we apply the sum of the forces in the y, that must be equals to 0. So the sum of the forces in the y is equals to 0. Upward direction is considered to be positive. Now there is, for the sum of the forces in the y, we can take FBC directly, because this FBC is in the vertical direction, and then we have to resolve this 120 Newton force into its x and y components, because this is our positive x, this is our positive y. So now this 120 Newton force is perpendicular with this handle axis, which is making 30 degrees. This is given that this is making 30 degrees. So now again, if I draw a line here, let's say if I draw a line here which is parallel to the axis of the handle, and this is making 30 degrees here, this is 30 degrees. So this force is perpendicular with this line, and if I draw another line perpendicular to this horizontal line, so this angle is now 30 degrees. So we can say that this force is making 30 degree angle with the vertical. So this angle is 30 degrees, and we can resolve this 120 Newton force into two components. So one of its component will be like this. This one will be 120 cos of 30, and it will have one component like one component in this direction. This one will be the sine component. So this is 120 sine of 30 degrees. So now these components are along the this one is along the x, and this one is along the negative y. So if we apply the sum of the forces in the y, that must be equals to 0. So we have ay in the positive y, so we will write plus ay. We have this FBC in the negative y, so you'll write minus FBC is 1385.64, and this cos component is in the negative y, so you'll write minus 120 cos of 30. This is equal to 0. So from this we can say that ay is equal to plus 1385.64 plus 120 cos of 30. So this is, we can say 1385.64 plus 120 cos of 30. So this is 1489.56. So ay is equal to 1489.56, and since we got the positive sign, this means that ay is acting in the positive y direction. Similarly, if we apply the sum of the forces in the x, so the sum of the forces in the x must be equals to 0. Towards the right is our positive x. Now we have ax in the negative x direction. This ax is in the negative x, so I will write minus ax. This sine component is acting in the positive x direction, so you'll write plus 120 sine of 30, and this is equals to 0. So we can say that minus ax is equal to minus 120 sine of 30. Minus will cancel out, and we will be left with x equals to 120 sine of 30. So this is equal to 60. So ax is equal to 60 Newton, and it is towards the right. This is in the upward direction. This is in the downward direction. So now we have solved for the first part. We have found the support reactions at A and the force in link BC. Now we were asked to find the internal loadings acting on the cross section passing through handle arm at D. So now we must pass a cutting section here, and then we must find the internal loadings. So let's say that this is now we have to pass a cutting section through D, and then I'm going to consider this particular part. So let me erase all this. So this will be our free body diagram. Now here, this is our point D. Now at point D, we will have, let's say, we will have the normal force. Let's say this is my normal resultant force, and D. We will have the shear force. Let's say this is the shear force VD, and we will have the bending moment. So let's say this is our bending moment in the clockwise direction, This is MD. So now to find ND, VD and MD, we are going to consider this free body diagram. So internal loadings through point D. So for that, if I apply the sum of the force in the X, and let's assume that now this is along the axis of the handle is our positive X, and in this direction is our positive Y. So this means that if we apply the sum of the forces in the X, that must be equals to 0. This is our positive X direction. Now VD is in the positive X. So we will say, let me show that this is our positive X and this is our positive Y. So VD is in the positive X, so we will write plus VD, and there is no other force in the X. So this means that the resultant internal shear force at the cross section through D is equal to 0 Newton. Similarly, if we apply the sum of the forces in the Y, that must be equals to 0. This direction is our positive Y direction. So we have ND in the positive Y, so I will write plus ND. And we have this 120 Newton force in the negative Y. So minus 120, this is equal to 0. And from this we can say that ND is equal to 120 Newton. Similarly, to find MD, if we apply the sum of the moment about point D, that must be equals to 0. Counterclockwise moment is assumed to be positive. Now we have assumed that MD is in the clockwise direction, so I will write minus MD. And this 120 Newton force is producing the clockwise moment, so I will write minus 120. And the perpendicular distance of this 120 Newton force from that point D is this 300 mm. So 300 divided by 1000 is 0.3. 300 divided by 1000 is 0.3. So 0.3 meters. So this is equal to 0, and we can say that minus MD is equal to plus 120 into 0.3. And if you multiply both sides with minus sign, so this will become positive, this will become negative. So 120 into 0.3, this gives us 36. So MD is equal to 36 Newton meter. We got the minus sign, so this means that MD is the internal bending moment at the cross section through D is in the counterclockwise direction. So MD is equal to 36 Newton meter, and it is in the counterclockwise direction. Now in this second problem, it is said that find the resultant internal loadings acting on the cross section passing through the handle arm at E. So now we have to pass a cutting section through E. So now for that we will again draw the free body diagram. Now we will pass a cutting section through E. So now this will be our free body diagram. Through E. This is our cross section now at E. And now at E we will have, let's say this is NE. We will have, let's say, the shear force in this direction. This will be our shear force VE. And let's say this is our bending moment in the clockwise direction. So now considering this segment, we will find the internal loadings through E. So internal loadings so again, this is our positive X direction. Our positive X direction is in this direction, and this is our positive Y direction. So again, if we apply the sum of the forces in the X, that must be equals to 0. This is our positive X direction. So we have this NE. This is in the negative X, so I will write minus NE. And there is no other force in the X, right? So this is equal to 0. So this means that the NE is equal to 0. The internal normal force at the cross section through point E is equals to 0. And the sum of the forces in the Y must be equals to 0. This direction is our positive Y direction. So we have VE in the positive Y. So I will write plus VE. Plus VE. And this 120 Newton force, this is in the negative Y direction. So I will write minus 120, this is equal to 0. Now VE is equal to 120 Newton. And we got the positive signs. This means that VE is in this direction. Similarly, to find ME, this is ME, we must apply the sum of the moment about point E equals to 0. Counterclockwise moment is assumed to be positive. So now we have assumed that ME is in the clockwise direction. So you write minus ME. And this 120 Newton force is producing the moment about point E in the clockwise direction as well. So you write minus 120. And now the moment arm of this 120 Newton force from that point E is this 300 plus this 100. So it's 400. So 400 divided by 1000 is 0.4. So 120 into 0.4, this is equal to 0. From this we can say that this is equal to, multiplying both sides by minus sign, we will get this as positive. So ME is equal to minus 120 into 0.4. This gives us 48. So ME is equal to minus 48 Newton meter. And the minus sign tells us that ME is actually in the counterclockwise direction at the cross section through E, and the magnitude is 48 Newton meter. Now in the last part of the question, we are also asked to find the internal loadings at the cross section of the short link BC. So as you guys can see that this link BC is a two force member. It is subjected to force at B and at C. So if it is applying the force on this handle in the downward direction, so this handle is applying the force on BC in this direction. So this means that this BC link is in tension. So at B, we will have the force on link BC in this direction, and at C we will have the force in this direction. So let me draw that link BC. This is our link BC. Let's say this is our link BC. This is point B, and this is point C. So at both ends it is subjected to force, that is the tension force. This is FBC, and here we have FBC, and we know magnitude of FBC, which is 1385.64. so 1385.64 newtons. Similarly, we have 1385.64 Newton. Now we want to find the internal loadings through the cross section of this short link. So we must pass a cutting section somewhere here, and then we have to consider the free body diagram. So let's consider the free body diagram. So this will be our free body diagram like this. And now here we will have, and let's say the normal force, and let's say we have the shear force, and we have, let's say, the bending moment. And let's say that this point through which we have made the cross section is, let's say, point P. Internal loadings for short link BC. Now if we apply the sum of the forces in the X, that must be equals to 0. So we have only this shear force in the X. So this means that the shear force is equal to 0. The sum of the forces in the Y must be equals to 0. Upward direction is considered to be positive. Now we have this N in the negative Y. We have this N in the negative Y. So we'll write minus N. And we have this FBC in the positive Y. So we'll write plus FBC, which is 1385.64. This is equal to 0. And from this, we can say that the normal internal loadings at the cross section for this short link is 1385.64 Newton. And similarly, if we want to find the bending moment, M, so we must apply the sum of the moment about point P equals to 0. Counterclockwise moment is assumed to be positive. So we have this internal bending moment M in the clockwise direction. So you write minus M. And as you guys can see that this FBC is passing to that point B. It's not going to produce the moment about point P. So there is no other moment. So this means that this is equal to 0, or we can say that the internal bending moment is equal to 0 for short link BC. So this is the solution of these two problems. I hope this will help you in your learning. Do subscribe Engineers Academy for the solution of such more problems from Mechanics of Materials by R.C. Hibbeler.